Hello everyone and welcome back to the channel. It is always great to sit down and chat with you all today. Today's date is August 21, 2026. It happens to be a beautiful Friday. So I hope you are all getting ready for a fantastic weekend ahead. Oh, I need to start by mentioning that I'm introducing a trending article from the archives today. I'm just hanging out here in the studio by myself, enjoying this really friendly and talking into the microphone like I usually do when I am deep diving into these amazing research papers. Before we get into the heavy science stuff, I have to ask if you know why the audio engineer got locked out of their house. It is because they forgot their key and could not find the right pitch to open the door. But I guess nobody ever understands my silly jokes anyway. So we will just move right along to the main event. The title is Finetuning Strategies for Terry Sounds by Vocal Imitation. The curl is Chatsinatsi, or the Doligoids Nabi 608.19,174. It is long, but it is packed with some truly fascinating insights that I cannot wait to share with you all. Let us start by talking about the core problem that this paper is trying to solve, because it is something that is actually quite visible to anyone who has ever tried to explain a sound to someone else. The concept is called query by vocal imitation, which basically means you want to find a specific audio sample in a massive database, and you do it by making a sound with your mouth to imitate what you're looking for. Imagine you are looking for the sound of a crashing car or a laser beam, and instead of typing out words, you just go whoosh or bang into a microphone. And the system has to figure out exactly what real-world sound effect matches your weird vocal noise. This problem is exceptionally challenging, mainly because of the extreme variability in how different human beings vocalize things, and the incredible acoustic diversity of actual sound classes in the real world. Human voices just do not have the same acoustic properties as metal crashes and digital synthesizers. So effective computer systems must learn complex representations that can bridge this massive modality gap between vocal sounds and non-vocal audio. Furthermore, these systems have to be incredibly robust, meaning the artificial intelligence needs to understand the underlying intention rather than just looking for an exact acoustic match. When we compare this new approach to older technologies, the differences are absolutely night and day. Because early approaches to this problem usually focused on simple late-use bottleneck features from basic autolineators, or they used moderately linear features combined with very traditional classifiers. Those older methods relied heavily on traditional similarity measures like dynamic time, warping, or basic listen distance, which struggled significantly because they were not adaptable enough to handle the sheer weirdness of human vocal imitations. More recently, researchers started using jartersted learning with neural audio embeddings, which were trained on massive datasets like Audioset, and this set a really strong baseline by utilizing large-scale neural networks to understand the context of sounds better. However, the authors in the specific paper wanted to push the boundaries, so they explored two complementary Finetuning strategies for a major audio engineering challenge, and they actually ended up creating the winning submission. Let me explain their brilliant strategies in detail, because the way they tackled this is just so smart and mathematically elegant. Their first strategy involved taking a pre-trained audio unit data, specifically a consistent ensemble distillation in order, keeping its core layers completely frozen while only training a lightweight projection head to max the buttons into a space suitable for retrieving sounds. By keeping the main brain of the network frozen, it prevented it from forgetting all the valuable general audio knowledge but it already learned from massive datasets, while still teaching it to specialize in matching vocal imitations to real reference sounds. A second strategy, which is the one that actually won the big challenge, built upon a modality architecture that integrated something called a triplet-based regularization objective. This means they used a hybrid learning strategy, where the system is not just rewarded for matching the vocal imitation to the correct sound, it was also explicitly penalized with matched the imitation to a known incorrect sound, especially using semi-hard negative examples. They'll gather a bunch of rejected vocal imitations and practice recordings, and they use these weird or bad imitations as structured negative examples to teach the system what a bad match looks like. They also used an amazing online augmentation methodology, meaning they artificially distorted the trained audio by shifting the pitch, stretching the time, adding random background noise, and randomly dropping out frames of audio to simulate the natural inconsistency of a human being who is out of breath or just making weird noises. They applied pitch shifting within a range of plus or minus 3 semitons, and injected low-amplitude Gaussian noise, which played a crucial role in improving the system generalization across completely different ventilation styles and poor recording conditions. Now, let us talk about how this incredible technology can be applied to everyday life, because the real-world applications are just absolutely mind-blowing when you think about them. Let us look at video editing and professional sound design, which is an industry where professionals currently spend countless hours throwing thousands of folders just to find one specific metallic click or wind swoosh. With this technology, a video editor could simply watch their video timeline, make a quick swooshing sound into the microphone at the exact moment the visual transition happens, and the software would instantly retrieve the perfect high-quality sound effect from a massive library. This would save hundreds of hours of tedious searching, and it would make the creative workflow so much more intuitive and directly connected to the human imagination. Second, we can apply this to advanced accessibility tools and assistive communication devices for individuals with physical or severe speech impairments. Some people might not be able to articulate standard words clearly for voice assistants, but they might be able to consistently produce specific vocal sounds, like hums or clicks or varied pitch noises. This technology could allow a smart device to perfectly map those unique vocalizations to specific daily commands, providing a much more flexible and inclusive way for people to interact with their environment without needing standard speech recognition. This could completely revolutionize how we interact with everyday smart home devices and music search engines in our living rooms. Imagine you have a melody or a specific beat stuck in your head, and instead of trying to figure out the lyrics of the artist, you just beatbox a terrible drum pattern or hum a weird bass line into your living room smart speaker. Because this model is trained specifically on machine vocal imitations using those clever and contrastive and triplet learning strategies, the smart speaker would actually understand the core vibe of your terrible beatboxing, and it would instantly pull up the exact song or genre you're thinking about. It bridges the gap between what is in our heads and what the computer understands, making technology feel so much more natural. And I just think that is one of the coolest things happening in audio research right now.